All right. In this video, we're going to go over a few of the questions that students had in terms of wanting more information on or clarification on. And really, there weren't too many problems or issues that students really raised besides really the idea of practice. So something that I saw kind of across multiple individual submissions are that really just needing to take time to practice and understand all the different formulas that are being used, needing to just do more ANOVA practice. And that's something that I really definitely highly encourage. Obviously, because statistics is one of those things that the more that you do it, the more that generally you'll understand it and see the common themes and how to do the calculations fairly well. Somebody said that they wanted additional information on paired samples. And so when we talk about paired samples, so think about the term paired. This is usually say that you are looking at person number one and they're paired with themselves in condition one and condition two. Same thing with person two, they're giving a value in condition one or at time point one, and then they're giving another value at time point two or condition two. And so the main idea with a paired samples t-test in this case is that the analysis that we're doing is going to be on these difference values. And the difference values are just going to usually be condition one minus condition two, or you can set it the other way. So C1 minus C2, meaning person number one's value in C1 minus their value in C2. And then we're going to be able to get a difference value. We're going to then be able to get the average of the difference values and the standard deviation of those difference values. And we're going to be able to treat this very similarly to how we did a one sample t-test. And so ultimately, our null hypothesis in a paired samples t-test is that the mean of the difference values is equal to zero, meaning that if you were to take all these difference values, add them up, and divide it by the number of difference values, you get zero. Think about what the difference value of zero means. Well, that means that that would mean that these two scores would be the exact same, right? If there truly was no difference. So if that was the same for everybody, then it would mean that, well, C1 and C2 really aren't doing anything. These conditions aren't different from each other whatsoever. The alternative is that this can be not equal to zero, meaning that it's some positive or negative value, or you can say that it's greater than zero or that it is less than zero, depending on the way that you're doing your subtraction and depending on the way that you believe the effect is actually going. So someone said that they had never seen the Bonferroni test before, and will we be using this frequently alongside the Tukey test? So when we're looking at post hoc tests, there are lots of different kinds. Two of the most common ones are the Tukey test and then Bonferroni. And it really kind of just depends on the researcher and what you want to use in your data analysis. Tukey is done by default in Jamovi. And for the sake of this class, just being able to illustrate post hoc tests, that is sufficient. But there are other types of tests like the Bonferroni, which is a little bit more conservative, where you would take your specific alpha value and divide it by the number. So the number of comparisons that you're using, or the number of comparisons that you're doing, and then you would treat that specific value as the new alpha value to use as comparison. There are lots of different other ones. And again, they vary to the degree to which they kind of protect against this type 1 error. Someone had a question on mean square variance. Now, again, when we talk about mean square variance, when we talk about mean square variance in like the ANOVA summary table, we have our source, sum of squares, degrees of freedom, mean square, and F. Mean square is just our sums of squares over degrees of freedom. And we've seen this before, right? So sums of squares over degrees of freedom is what gives us our variance. Now, let's look at this formula for a little bit, right? So we're adding up all of these squared deviations, and we're dividing by the degrees of freedom. Degrees of freedom is just n minus 1, okay? So remember that when we're talking about variance and we're talking about standard deviation, we're wanting to look at the average amount of deviation, right? And so when we talk about the average of something, we typically are going to sum up that thing and divide by the number of things we've added up. Well, this kind of formula looks very similar to this, right? We're adding, summing all these things. So again, we're adding all these things and we're effectively dividing by the number of those things. But just remember, we use degrees of freedom so that we have a better estimate of the population variance. Well, this is where this term mean square comes from. So what's the square in this term? Well, these are all these square deviation values. When we talk about mean, we're essentially talking about an average. The average squared deviation is known as the variance. And then when we square root that variance, so square rooting the variance will give us the average deviation, which is the standard deviation. Another person had a question on how to interpret eta squared in terms of effect size. Generally speaking, when we're looking at eta squared, this is going to be a value that ranges between 0 and 1. And then we multiply that by 100 to give us a specific percentage. And so the way that we interpret this is we can say that blank percent, so whatever our value for eta squared is, we can multiply that by 100, which would give us a percent. And we can say the percent, so something percent of variability or variance in our dV, in what we're measuring, can be explained by, and then we have our independent variable. So let's say that we are looking at type of diet, and we have 3 different types of diet: a control diet, a high-fat diet, and a low-fat diet. And we find that the eta, and we're measuring, let's say, time to escape a maze, where lower times mean that the animal is quicker. So let's say that the eta squared is 0.48. The way that we would interpret this value based on our variables is we would say that 48% of the variability in, and again, what's our dependent variable, in time, in seconds, to escape, can be explained by, and then what is our independent variable here? Well, our factor is diet. So we can say by type of diet. Now, eta squared will never be 100% for pretty much any experimental research, mainly because there's always going to be other things that could be influencing that relationship. Other kind of questions, again, relating to what I had mentioned here in the beginning, is just kind of practice. So for instance, a lot of the formulas, right, for solving for sums of squares in ANOVA, we have this cool formula here: sum of x sub k squared over n sub k minus sum of x's squared over n, right? And being able to remember that depending on however many levels, or k, we have for our factor, that's going to be the number of components this particular bracket term will have, making sure that we are keeping organized our sums of x's, our sums of x squareds, our capital N's, lowercase n's. These are very important to do, but also why I encourage extra practice, but also why I give exams as take-home exams, so that students can be able to take that little bit of extra time to make sure that they are understanding and using these formulas appropriately. So those are all the questions and concerns that students had for this how are we doing assignment. And again, feel free to reach out to me if you have any others.